Welcome to Study Loop.
So here is a conductor whose dimensions are given. Current I is sent through the conductor, and the conductor is placed in a magnetic field. Due to the force due to magnetic field, the charge carriers here, they get separated, right? So depending upon their polarity, so positive charges get on one side and negative charges get on the other side, right? And hence how voltage is developed in across the width of this conductor. That is what we have to find. So here is given the Hall voltage is 10 microvolts. So on the basis of the Hall voltage, we have to find out what was the drift velocity of the charge carriers. So first, let us go to the root. The drift in the Hall voltage V is due to the electric field across the width, that is E times electric field times D, where the distance D is the distance of the width, that is equal to 1 cm. This is equal to 0.01 meters in SI, right? So the electric field is due to the force due to magnetic field FB by Q times D. Now the force due to magnetic field, considering that the magnetic field and the velocity of electrons are perpendicular, this is simply BQV upon Q times D. This is V. So from this equation we get velocity V is equal to Hall voltage upon magnetic field that is applied times the distance across which the Hall voltage was seen. So this is equal to, we know the value of V, right? This is equal to 10 microvolts is equal to 10 to the power minus 5 volts in SI. We know the value of B, we know the value of D. So just plug these three values in here. So this will give me the velocity is 6.67 into 10 to the power minus 4 meter per second. So we found the velocity of the charge carriers, right? Now, and this is which part? This is part A of the question to find out the drift velocities. Now, what is the number density of the charge carriers? So to find the number density of the charge carriers, we need to see the relation between current and the drift velocity. The current across the conductor I is equal to drift velocity times charge of electron times number density of charge carriers times the cross-sectional area, right? So uh, N is equal to I upon B E A. So current is given, I is given. The drift velocity we calculated in part A. We know the charge of an electron 1.6 into 10 to the power minus 9 tin, and the surface area is what? The cross-sectional area is, this is the cross-section, right? So that is 1 into 10. So 1 cm is equal to 0.01 in meters, and 10 micrometers is equal to 10 to the power minus 5 meters. Seems like one of the lengths is equal to the V, right? Equal to V. Okay, no problem. Just forget that. Now just plug in the values of I, V, E, and this is already given. So this will give me the value of N to be 2.81 into 10 to the power 23 number of charge carriers per meter cube. All right. Okay. Now let's move. This gives me part solution to part B of the question. Now part C asks us to show in the diagram the polarity of all potential difference, which is as in current. Okay. So we consider that the current is flowing this downwards, which means we consider current to be positive. So electrons are moving upwards, right? So this is the direction of electron, right? Now if you use the right hand rule, then if the charge carriers were positive, they would get force, they would experience force on the right, on the left hand side, and if they are negative, they would experience the force on the right hand side. So since they are electrons here, so force will be along this side. So we will have negative charges all around in this region, right? And positive charges will be along this region. So this is the polarity. So V is positive along in the left hand side, whereas V is negative in the right hand side. So this gives the polarity of the potential difference. And this ends the solution for this question. Thank you for watching.